Question about Doppler effect using the formula. An ambulance travels along a straight road at a speed of 30 meters per second. Its siren emits sound of frequency 2000 hertz. The speed of sound in the air is 340 meters per second. The ambulance passes a man standing at the side of the road. What is the frequency of the sound heard by the man as the ambulance moves toward him and as the ambulance moves away from him? So here is an audio example. The sound is getting intense. The frequency is getting higher. Sounds like it's fading away. So as you notice, there is a change in frequency. This change in frequency is because the relative motion of an observer and the sound source. To understand the formula, first let's identify a couple things. This is a moving sound source towards this stationary observer. As this source is approaching the observer, the frequency heard by this observer is higher. So it's a higher pitch because it's compressing all the air, making the wavelength shorter, therefore the pitch go higher. So in this case, the frequency is gradually increasing, and after pass by the observer, now the frequency is gradually decreasing. So there are two main characters in this story. One is the observer, and the other one is the sound source. The sound source is going to emit a sound with a frequency that I'm going to call frequency of the sound source. And this frequency depends on the location with the observer, is going to be perceived as a FO, or frequency heard by the observer. Now, because the observer is stationary, so the speed of the observer is 0, and the speed of the sound source will be defined in the problem. And there is one third thing that we need to pay attention is the speed of sound in the air. So these are another factor, because the speed of sound in the air depends on the medium, is going to carry the sound, is going to propagate the sound with certain specific speed. Now this is the Doppler effect formula. So FO is the frequency detected by the observer, is equal to the frequency emitted by the source, and multiplied by this fraction. V is the speed of the sound in the median over the speed of the sound in the median, same number, plus minus the speed of the sound source. The plus minus in this formula indicates that it can be used for one of those two situations, when the sound source is approaching the observer and when the sound source is going away from the observer. So let me use this formula in this question to understand when to use the plus and when to use the minus. So the frequency heard as the ambulance moves towards the man, I'm going to use this space to calculate, and the frequency heard as the ambulance moves away from the man. Now I need to go back to the question to identify all the variables. So the ambulance is traveling with this speed. So this is the speed of the source. 30 meters per second. Now, its siren emits a sound of the frequency of 2000 hertz. So this is the frequency of the source, emitted by the source. The speed of the sound in the air is 340 meters per second. So this is the speed of the sound. I know it's confusing because you have the speed of the source and the speed of the sound. So the speed of the source is that the source that is emitting sound. In this case is the ambulance, siren. The speed of the sound that propagates in the median, in this case is the air. So that is 340 meters per second. Okay, so look at this formula here. So I have Fs, which is this. I have the speed of the sound in the air, which is this. And I have the speed of the source, which is this one. So I use all the variables and set up both equations the same way. The only thing that is missing is the plus minus sign. So if the sound source is moving toward the observer, the sign here is negative. And if the sound source is moving away from the observer, the sign here is positive. Now let's calculate. 340 minus 30 is 310. And 340 divided by 310 is this number times 2000. So the frequency detected by the observer is 2193 hertz. And on the other side is 340 plus 30 is 370 on the denominator. So 340 divided by 370 is this number times 2000 is the frequency is lower, which is 1837 or 38 hertz. So now let's find the best match for this and this. So toward looks, we have two candidates here. This is less, this is more. I will pick this one. Let's see on the other side. So when it's going away is more like this one. So the answer is option D. Another formula application. A source of sound of frequency 1000 hertz directly approaches a stationary observer. The observer measures the frequency of the received sound to be 1500 hertz. The speed of sound is in still air is 330 meters per second, which means that it's not windy. What is the speed of the sound? I'm going to rephrase. What is the speed of the source of sound? So this is the sound source that is emitting a frequency that is Fs is 1000 hertz. And this is an observer. So if the front of this sound source is, the waves are compressed, so the back is spread out. And what else is saying? Okay, the observer is going to receive the sound, so FO, F the observer is 1500 hertz. The speed of sound in the air is 330 and is asking Vs. For simplicity of the equation, I'm going to label plain V, val sub, the speed of sound in the median, in this case in the air. Okay, remember now, because the sound source is moving toward the observer, then we are going to select the negative sign. Negative, not positive. Doing our substitution, FO is 1,500, FS is 1,000, and the speed of sound in the air is 330, and this is, sorry, 330 negative Vs. So we can divide both equations by 1,000, so you'll be 1,500 over 1,000, and this 1,000 will not be there, so 330 over 330 minus Vs. So then you'll be 1.5 is equal to 330 over 330 minus Vs. So now doing kind of cross multiplication here, so you'll be 1.5 330 minus Vs is equal to 330. Now 1.5 times 330 is 495, and 1.5 times minus Vs is minus 1.5 Vs is equal 330. Okay, so now my minus 1.5 Vs is 330 minus 495, and minus 1.5 Vs is equal to minus 165. Now divide by negative 1.5. Negative is 110, so 110 positive, 110 meters per second. So that is the speed of the sound source, which is option A. Doppler effect using graph analysis. A source emitting sound of a single frequency Fs travels at constant speed directly towards an observer. The source then passes the observer and continues to move directly away from the observer. The velocity of the sound remains constant. Here is a visual illustration. As you heard, was a gradual increase of frequency and then a gradual decrease of frequency. If the transition was gradual, I would eliminate A and B because it looks a big shift here. So in real life, does not work like this. So it's kind of gradual transition. So those two, bye-bye. The intersection on each graph indicates where the frequency changes from higher to lower or lower to higher. Now in this graph indicates that the frequency detected by the observer is high as the source is approaching, and then is going to change to lower, then to lower to the frequency of source. Now in this one here indicates that the frequency received by the observer is lower than the frequency of the source as it approaches the observer, and this is not correct. So this one is best describes the situation of the Doppler effect when a sound source passes by a stationary observer. So answer is D.